Hey everyone, in this video let's go to question 863, all nodes distance k in binary tree on Leetcode. This is part of our blind 75 list of questions, so let's begin. In this question we're given the root of a binary tree, the value of a target node target, and an integer k, and we want to return an array of all of the values such that they have a distance of k from the target node. We can return our answer in any order. Okay, so let's take a look at what this is saying here. So our node here is 3, our target, our root here is 3, then our target here is 5, and our k is 2. So essentially, if you think about it, this is an undirected type graph, right? So it's not just the children that we can go down, but we can also go up to the parent and then sideways like that. So it's undirected in that manner. Okay, so distance 2 from this 5, well, technically this 1 is, right? Because you can go here and then here. So this is distance 1. And then this 2 and then here, this is distance 2. And then this 2 and then this 4 here as well. This is also distance 2. So we would return 7, 4, 1. Again, we don't have to return in the same order. If this was something like distance 1, then we would return 6, 2, and 3. For something like this, where we just have one item and like k is actually larger than we can even traverse. Like for example, maybe we're over here and we want to return k of 5. Well, there's no nodes that are like 5 distance away, right? The maximum is 1, 2, 3. So we can't really do anything like that. So that's the question, and we have the constraint here that all of the nodes values are unique. Okay, so how might we go about doing this problem here? Well, this is a binary tree type problem. So whenever we notice a binary tree, and I actually mentioned that this is a graph type problem because if you think about it, this is an undirected graph, right? Because we can go from the 5 to the 3. So realistically, maybe you can think of this as a graph problem rather than a binary tree problem. So in a graph problem, what can we do? Well, first of all, we need a way to like understand the graph, right? We need a way to understand our graph. And we have a couple of ways of doing this. The way that I usually use is adjacency list, because I need to know like what are the neighbors of 5, right? What are the neighbors of 3? What are the neighbors of 1? And if you actually take a notice here, in this case here, the neighbors go two ways, right? The neighbors go two ways because it's an undirected graph. So what that means here is that actually 5 is connected to 3, but also 3 is also connected to 5. And similarly, 3 is connected to 1, and also 1 is connected to 3. And we can see here that we actually have no cycles because this is a binary tree, so we don't have any cycles. But basically, we have a two-way connection here. So I think first thing we actually need to do is, even before we discuss our algorithm, we need to figure out a way to like create this adjacency list, right? Now, it would be easy if like we just had one way, right? But since we have two ways, we have to be a little bit more clever in how we do this. So let's take a look at how we can actually form our adjacency list. And actually here, like if you think about it, our adjacency list, maybe what we can do is we can start a DFS call from this 3 over here, and we can go down. And so what am I saying here is we can start a DFS call from the root, and then we can go down. And so then I have this 5 here. So what do I notice? Well, I notice that there is a connection from the 3 to the 5, but then also what I can do is I can add in a connection back from the 5 to the 3. And then I can also do the same thing for my one child over here. So let's go ahead and see how we can at least do that, at least create the adjacency list. So in that case, what do we need? Well, adjacency list in Python, the way I always do it is I have adjacency list, and it is a default dictionary of a type list. And then I want to create my adjacency list using a DFS call. So that's what I would do. So my helper here is my DFS helper. Now what do I need? Well, essentially all I need really is the root, right? So I need the node and I need the adjacency list. That's all I'm doing here. You can just think of it as like we want to do maybe an inward traversal or anything like that, any type of traversal. And as we're doing the traversal, we will create our adjacency list. Okay, so let's say initially our node is passed in as 3, right? Our node is passed in as 3. Now what can we do? Well, I need to check if we have a left child and we have a right child. And if we do, then I'm going to create these two connections. So how can we go about doing that? So let's take a look. If node.left, right, pass. If node.right, pass. Now, if node.left what? Well, now I need to create a connection from the node, which is like the root here, to this child here. And I need to create one back. So what can I do? I can do adjacency list at node dot append. I can do dot append because we made it a list here. So dot append, we will do node dot left. And then we will do the same thing backwards. Adjacency list node dot left dot append node. And then we'll do the same thing but on the right hand side. So adjacency list node dot append node dot right. And then the same thing backwards. Node dot right dot append node here. Okay, So now we've created these two connections, right? We've created a connection from 5 to 3, and we've created these two connections from 3 to 1, and then also from 1 to 3. Now what? Well, now we need to actually go ahead and recurse on these two things here, right? Because we want a connection from 5 to 6, and then 6 to 5, also from 5 to 2, and then 2 to 5, etc. And we want the same thing on this side over here. So what I can actually do is I can just do my self.helper, node.left, adjacency list, and self.helper, node.right, adjacency list. Now, you may actually notice a problem here because if we go all the way down to the root, right, or all the way down to a leaf, it really has no children, right? So we actually don't even want to do a DFS call in this place. So we can just surround this by something like if node.left, then I will go ahead and do this. If node.right, then I will go ahead and do this. Alternatively, we could have just kept this and then like maybe something like if not node, then return, but I think I'll just leave it at this spot here. Okay, so now we have our adjacency list. Now the question is how do I basically like figure out all of the nodes that are distance k away from my target 5? Like how do I do that, right? So if you kind of think about it, we've done questions like this before, right? And really here, what I'm kind of leaning towards is a BFS type approach. Why BFS? Well, we know in BFS what we do is we start off at a specific index or a specific node and we expand breadth first. We expand level by level, breadth first outside. So if you kind of think about it in terms of something like this, we're over here, then we can expand breadth first. The initial time we expand, like on our first iteration, these three will be the nodes that I will go ahead and add to my queue. The second time I do my breadth first search, what will I add? Well, I will add in these three nodes here. And you can kind of notice that these three nodes here, they're actually our answer. They're level 2 away. They're 2 nodes away from our root. So essentially, like breadth first search is also easier way in which we can do this compared to depth first search. In depth first search, we can definitely do it, but then we would have to go through all of these nodes, and then we would go backtrack, and then we would go through this one, and then see that this has no children, and then backtrack, and then go here, and then go down, backtrack, go here, go back, etc. So depth first search would still work, but it's often the more like difficult approach here. Breadth first search is always preferred here when you want to like traverse level by level. So let's just take a look at how we can do the breadth first search approach, right? Because we have all of these connections here. And so I can do this. I can go ahead and add this on my level 1 breadth first search. I can add this on my level 2 breadth first search. And really, when I'm arrived at level 2, I will just return whatever is in the queue. And so that will be this answer over here, right? So let's take a look at how we can do that. And we've done questions like this before using queue and kind of like this level by level approach. I believe we've done the question, what was it called? Let me see if similar questions has something. Okay, so it doesn't have it. I believe it was called when you had to go from like one word to another, where like maybe you had to go from pog all the way to like log, and you want to find the fewest amount of ways you can do this. I think there's a question like that. Word ladder, yeah, that's what it was called. So we've done a question like this similar, but anyways, let's take a look at how we can go about doing this. What do we need? Well, in breadth first search, we always have a queue and we have a scene set. Now, what do I want to add to my queue? Well, I want to add the target, right? I want to add the target because that's where I'm starting off at. So I will basically just append the target and I will add it to my scene set. And now what? Well, now I need to go ahead. I will do while queue. And actually this helper call here, let's just go ahead and fill this out. So this will populate our adjacency list. What do we need to pass in? We need to pass in the root and adjacency list. And root actually cannot be null, so we don't have to worry about that case. Okay, so we have this. Now what do we need to do? Well, we have our queue, right? And now what we want to do is we want to process level by level. What does that essentially mean? Well, think of it like this. Like, let's say we had the following binary tree, right? Like maybe we had, actually I'll draw it like this. Let's just say we had the following. Maybe we had something like this, right? Let's say we had this binary tree, and this is our connections over here. Now, if I'm adding this into my queue, right, this binary tree into my queue, initially, what will I have? Initially, I'll just have this one node inside of the queue, and I can kind of refer to this as level 0 or level 1, depending on like what you want. Now, I will go ahead and add the left 2 children. So this will be like a new level, right? This will be a new level. Now, notice that when I add this child over here, I'm going to actually process it, right? Because queue is first in, first out. So I will process this, and I will actually also add in these two onto my queue. So if you kind of think about it, what's going to happen is that these 3 indices here, like, or these 3 nodes here, will be on the queue at a single time, right? Because what happened is that I process the node, I process the root, so I forget about the root. But when I process the root, I go ahead and I add these 2 children, Okay, so I add in these two children, and this is what's in my queue right now. And then I go ahead and I process this one, which means I will add in these two children. But now notice the queue actually contains all three of these, right? The queue contains all three of these. But we will not consider all three of these as part of the level, as part of like one iteration of the queue. We will only consider these two elements here. How do we do that? Well, when we are starting our breadth first search, we will basically just look at the size of the queue and we would just process that many elements. It's perfectly all right if we add in more elements, but we will only process the amount of elements on the queue, which here correspond to the level. So what that kind of looks like, and again, we've done a question like this in the past, so take a look at it, but what we can do is we can do size is equal to length of queue, and then I will only process the elements such that they add up to size, right? Or that we only process size amount of elements. Okay, so what can I do here? Well, I can go ahead and I pop from my queue. And so now what I've done is I've popped from my queue. So maybe I've popped the number 5 here. So now I want to add in all of the neighbors. I want to add in the neighbor 3. I want to add in the neighbor 6. I want to add in the neighbor 2. So I can do for adjacency list, or I get for node in adjacency list at cur. Then I want to go ahead and add this. But I only want to add this if I haven't seen it before, right? This is how we do our BFS. So we can do if node not in scene, then we can add it to our queue. And we can add it to our scene. And why do I need this scene here? Well, I need the scene because if you think about it, if I'm arrive at this 3, right? Let's say I'm processing this 3. I don't want to again add the 5, right? I don't want to again add the 5, or it's just going to go back and forth, back and forth. So I only want to essentially move forward. I don't want to add the same node again. That's why we need the scene. Okay, so we have that information. Now, we're almost actually done, but we just need to figure out how do I know when I'm arrive at my answer? If you think about this, every time we do one of these calls here, like every time we process a level, that's like one level gone from this k over here, right? So the first time I process this, I will have processed nodes 6, 2, and 5. So now if you think about it, from this level, my k decreases by 1, right? Because from this level, now I just need to look one level further. So what I can do is I can do k minus equals 1, okay? So we keep doing that, and then eventually we will add in these 4 elements here. And so at this point, k will be 0, right? And so then I can actually just check. I can check if k is equal to 0. Let's just go ahead and maybe we can break. And then if I break, what do I have on my queue? Well, I have these elements left. Like I haven't processed these elements. These are the elements that are left on my queue. So then I can just go ahead and return. Maybe we'll do like node.val for node in queue. And so this essentially is my solution. So let's go ahead and run this. We'll go ahead and submit it. And we can see that it works. Just to, again, kind of illustrate like what we did over here, every time we process a level, so if I go all the way back here, every time we process one of these levels, so when I process this first level, my k now becomes from 2, it goes to 1. And now when I process this one here, when I process this one over here, then essentially it goes from, I made a mistake here. Actually, when I process this first 5 over here, then from here, my k goes from 2 to 1, right? So my k goes from 2 to 1. Okay, and let me actually make this smaller. So my k goes from 2 to 1. And when I process all of this over here, my k goes from 1 to 0. And notice that when I process all of this, I'll be adding on these values onto my queue, but I won't process them because we only process 3 nodes, right? And so when k is equal to 0, then I know that whatever is on my queue must be k distance away from the target. And so that's how we do this problem. What is the time and space here? Well, the space, you can kind of think of it as just the number of nodes on the tree, right? That's the space. Now, for the time, what is the time here? Well, if you think about like, we have to consider all the types of connections, right? So it's just like the amount of edges plus the vertices. So that's like what you can think about in terms of the time complexity. Okay, thanks for watching.